Welcome to Lecture 6 of Advanced Topics in Quantum Information Theory. This will be the first of a few lectures on the topic of non-local games, and in this one we'll introduce the non-local games model, and then we'll focus on a special class of non-local games called XOR games. We'll prove a theorem known as Tsirelson's theorem, which tells us a great deal about XOR games, and we'll see some implications of this theorem in the next lecture. Let's begin with the non-local games model. A non-local game is a hypothetical game played by two participants, Alice and Bob. Alice and Bob are cooperating in this setting, and they will either win or lose as a team. The game itself is run by a referee who isn't a player. The referee's actions are completely dictated by the specific non-local game that's being played. The first step of a non-local game is that the referee sends a pair of questions, XY, to Alice and Bob. Alice receives X and Bob receives Y. The questions are sent to Alice and Bob simultaneously, and you should imagine that the two players are separated and cannot see the question asked to the other player. More generally, we're typically interested in the situation in which Alice and Bob are forbidden from communicating with one another once the game begins, but the specific constraints on Alice and Bob's behavior will be formalized later, depending on the types of strategies we're interested in. In any case, Alice must respond with an answer A, and Bob must respond with an answer B. Each possible answer pair, A-B, is either a winning or a losing answer pair for each pair of questions XY, and upon receiving Alice and Bob's answers, the referee will declare that they either win or lose. Now, there are many interesting aspects of this model and many questions that you can ask about it, even in a completely classical setting, which happens to be very much relevant in complexity theory as an abstraction of two-prover, one-round interactive proof systems in particular. In the setting of quantum information and computation, however, the non-local games model is principally used as a tool through which quantum non-locality is studied. And in particular, it is the possibility for Alice and Bob to share a quantum state and to perform measurements on the state in order to correlate their answers in interesting ways that gives the model a unique quantum information theoretic character. Now let's be more precise about how non-local games are defined. When we wish to formally define a particular non-local game, there are 6 things that need to be specified. First, we need to say exactly what are the sets of possible questions and answers. These must all be finite and non-empty sets. X is the set of possible questions for Alice, Y is the set of possible questions for Bob, A is the set of possible answers for Alice, and B is the set of possible answers for Bob. Next, it is assumed that the referee randomly selects the pair of questions XY for Alice and Bob from a given distribution, and we will let pi be the probability vector that describes this distribution. Finally, we must specify which answer pairs win and which answer pairs lose for each pair of questions, and this information can be described as a predicate V. Specifically, V of AB given XY equals 1 when AB is a winning answer pair for XY, and V of AB given XY equals 0 when AB is a losing answer pair for XY. And once we have those 6 things, the 4 question-answer sets, the distribution of question pairs, and the predicate that describes the winning and losing answers, we have formally described a particular instance of a non-local game. Some non-local games are more interesting than others, but we are free to consider whatever non-local games we wish according to this definition. Notice that the definition of a non-local game doesn't say anything about Alice and Bob's behavior, which is something I already alluded to. We may consider different sorts of strategies based on classical information and quantum information, as well as more abstract notions of strategies, such as no-signaling strategies, and we'll get to that later. But for now, you can intuitively think about the inability of Alice and Bob to communicate with one another as being the principal challenge they face when trying to win a non-local game. Here's an example of a non-local game, and at least in the setting of quantum information, it's the most famous example of a non-local game. It's called the CHSH game, named after Clauser, Horn, Shimoni, and Holt. And it's essentially just a game-theoretic way of describing the CHSH inequality, which is the most common example of a Bell inequality. All of the question and answers are binary values, so x, y, a, and b are all equal to the set containing 0 and 1. The probability vector pi is uniform over the 4 possible question pairs, and the predicate v takes the value 1 if and only if the exclusive OR of a and b equals the AND of x and y. That is, if the referee asks any of the question pairs 0, 0, 0, 1, or 1, 0, then Alice and Bob win if their answers are the same, and if the referee asks the question pair 1, 1, then Alice and Bob win if their answers are different. Another example of a nonlocal game is the FFL game, named after Fortrow, Feige, and Lovász, and we'll see one reason why this game is particularly interesting in the next lecture. In this game, the questions and answers are again binary values, and this time the probability vector pi is uniform over the 3 possible question pairs 0, 0, 0, 1, and 1, 0, so the referee will never ask the question pair 1, 1. The predicate takes the value 1 if and only if the OR of a and x is different from the OR of b and y. Alternatively, if the referee asks the question pair 0, 0, then one of the 2 players, but not both, must answer 1 in order to win. And if the referee asks the question pair 0, 1 or 1, 0, then the player that receives the question 0 must answer 0 in order for them to win, and it doesn't matter what the player who receives the question 1 answers. So, if you're playing this game and you receive the question 1, then it doesn't matter what you answer. But if you receive the question 0, you're not sure what to answer, because you don't know if the other player received 0 or 1. The last example of a nonlocal game for this lecture is actually a class of games, and although we won't discuss this class of games further, it is a good example because it demonstrates that nonlocal games can have large question and answer sets, and it illustrates how nonlocal games can be connected to other fundamental concepts, in this case graph coloring. Imagine that we have a simple undirected graph that has at least one edge, and let's assume for simplicity that the vertices of the graph are numbered 1 through n. Let's also suppose that k is a positive integer, and think of the numbers 1 through k as representing distinct colors. The way the game works is that the referee sends each player the name of a vertex, and they must respond with a color. With probability 1/2, the referee chooses a vertex uniformly at random and sends this same vertex to both players. Otherwise, the referee randomly selects an edge from the graph and sends the 2 vertices incident to this edge to the 2 players. If the players receive the same vertex, they must respond with the same color in order to win, while if they receive adjacent vertices, they must respond with different colors. So you can imagine that the players are trying to convince the referee that a given graph is k-colorable. Next, we will introduce a few different strategy types for nonlocal games. In this lecture, we will discuss 3 types of strategies, and in a couple of lectures, we'll discuss an additional type. We'll begin with deterministic strategies. In a deterministic strategy, Alice and Bob answer functionally, meaning that Alice's answer A is given by a function f of her question x, and Bob's answer B is given by a function g of his question y. That's simple enough. It's a very simple and intuitive notion of a strategy, and it's completely classical. We can also consider randomized strategies in which Alice and Bob still play classically, but may use randomness when choosing their answers. This can be randomness that can be generated individually, or they could make use of shared randomness. Either way, we can always view any randomized strategy as being equivalent to the random selection of some deterministic strategy, according to an arbitrary probability distribution over deterministic strategies. Finally, entangled strategies are strategies based on quantum information. In an entangled strategy, Alice and Bob share a quantum state rho of 2 registers A and B, with Alice holding A and Bob holding B. For each possible question that one of them receives, they have a measurement, described in the usual way as a collection of positive semi-definite operators that sum to the identity. Alice's measurement operators are labeled by the letter P, and Bob's measurement operators are labeled by the letter Q. The superscript on each measurement operator refers to the question, and the subscript refers to the answer. So, for a given pair of questions xy and a given pair of answers ab, we see that the probability with which they answer xy with ab is the inner product of pxa tensor qyb with the shared state rho. It's important to note at this point that we're not placing any restrictions at all on the sizes of the registers A and B, other than that these are finite-dimensional quantum systems. Although technically rho is not required to be entangled, it turns out that if rho is separable, then any strategy of the form just described that makes use of the state rho will be equivalent to a classical randomized strategy. So the possibility that rho is entangled is what makes this type of strategy interesting. When we speak of the value of a nonlocal game with respect to any class of strategies we might be interested in, we mean the maximum or the supremum of the probability that Alice and Bob win, taken over all strategies in that class. The classical value is simply the maximum winning probability taken over all deterministic strategies. We denote the classical value of a nonlocal game G as omega of G, and this value can be expressed as you see here. The maximum, naturally, is over all deterministic strategies, or equivalently, over all functions f from x to a and g from y to b. And the expression that we're taking the maximum of is a simple formula for the winning probability of that strategy. By the way, we would get exactly the same value if we were to maximize over all randomized strategies rather than deterministic strategies. That's because a randomized strategy can be viewed as the random selection of a deterministic strategy, and we can never achieve a higher value by averaging than we could by simply taking the maximum. So, given that we don't need to differentiate between the deterministic and randomized classical values of nonlocal games, we simply refer to their classical value. The entangled value of a nonlocal game G, which is denoted omega star of G, is the supremum winning probability taking over all entangled strategies for that game. The expression written on the slide is the winning probability for any one given entangled strategy, represented by the state rho and the measurement operators pxa and qyb, and taking the supremum over all possible strategies yields the entangled value. It is important that we take the supremum, as there are nonlocal games for which the entangled value is never actually achieved. We can only approach this value with a sequence of strategies that make use of larger and larger shared entangled states. It was, in fact, an open question for a long time if there were nonlocal games like this where the quantum value is never achieved. The question was resolved affirmatively in 2017 by William Slofstra. Let's briefly go back to the examples of nonlocal games we saw previously, specifically the CHSH game and the FFL game, and discuss their classical and entangled values. For the CHSH game, the classical value is 3/4. One way to argue that is simply to go through all of the deterministic strategies and to verify that 3/4 is the highest winning probability. There are 4 possible functions from 1 bit to 1 bit, and 2 players to consider. So there are just 16 deterministic strategies in total. In general, we can always do the same thing and just enumerate the deterministic strategies to see what the maximum winning probability, or in other words, the classical value is. But naturally, this becomes highly impractical as the number of questions and answers grows. In this case, though, it works. The entangled value of the CHSH game is cosine squared of pi over 8, which is roughly 85%. It isn't too hard to explicitly describe an entangled strategy that achieves this winning probability. It's enough to use 2 qubits in a maximally entangled state, and to choose appropriate measurements for Alice and Bob to make it work. And possibly you've already seen such a strategy, given that this is such a well-known example. But this doesn't actually show that there's no better entangled strategy. And anyway, we'll see that Tsirelson's theorem, which is coming up later in the lecture, provides us with a very simple way of verifying that the entangled value of the CHSH game is cosine squared of pi over 8, This and other applications of Tsirelson's theorem will be covered in the next lecture. Turning to the FFL game, we find that the classical and entangled values are in fact equal for this game. They're both equal to 2/3. That might give you the impression that the FFL game isn't all that interesting, but it actually is pretty interesting, as I suggested before, and we'll discuss that in the next lecture. And it's also healthy to recognize that entangled strategies aren't always strictly better than deterministic strategies. Here they don't provide any advantage at all. To prove that the deterministic value is equal to 2/3, one may again simply check all 16 possible deterministic strategies. There are various ways to prove that the entangled value is also 2/3, and one way to do this is to prove that the value of this game is 2/3 even for so-called no-signaling strategies, which are a larger class of strategies than entangled strategies, and they can be very easily analyzed through the use of linear programming. Next, we will discuss a restricted type of nonlocal game called XOR games. An XOR game is a nonlocal game in which Alice and Bob must answer binary values, and moreover, the predicate v must have the special form that's shown here. Specifically, there must be a binary valued function f such that for every pair of questions xy, Alice and Bob win if and only if the exclusive OR of their answers a and b agrees with f of xy. Thus, all that matters is whether or not Alice and Bob's binary valued answers agree or disagree, and the function f tells us which of the two alternatives is correct and which is incorrect. Notice, by the way, that it's always the case that one of the two possibilities, agreeing or disagreeing, is correct and the other is incorrect. Such a game is uniquely determined by the question sets x and y, a probability vector pi on question pairs, and the function f just described. So, when it's convenient, we can identify an XOR game with these four objects, x, y, pi, and f. For example, the CHSH game is an XOR game. The question sets are both binary values, the probability vector is uniform, and the function f is the AND of x and y. The FFL game, on the other hand, is not an XOR game. It just doesn't fit into the framework. When we analyze XOR games, it's often convenient to speak of the bias of an XOR game, or of a strategy for an XOR game, rather than its value. The bias essentially just refers to the probability of winning minus the probability of losing. So, when we speak of the bias of a particular strategy, this is what we mean: the probability that it wins minus the probability that it loses. And when we speak of the bias of an XOR game, we simply mean the maximum or supremum bias over all strategies being considered. It's not too hard to see that the bias of a strategy is nothing more than twice the probability that the strategy wins minus 1. This is because the probability that a strategy wins plus the probability that it loses is always 1, and so the probability of losing is just 1 minus the probability of winning. And performing this substitution into the definition of the bias reveals this simple formula. Likewise, the bias of an XOR game is simply twice its value minus 1, for exactly the same reason. We'll denote the classical bias of an XOR game G as epsilon of G, and the entangled bias as epsilon star of G. And so the expressions you see written here are true. To be clear, the bias doesn't reveal any new information about a game beyond its value. It's just convenient when analyzing XOR games to work with the bias rather than the value. Now suppose that we have an XOR game G, which can be described by the question sets x and y, the probability vector pi over question pairs, and the function f that determines the referee's predicate, as we discussed a few moments ago. Let's also suppose that we have an entangled strategy for G, which is determined by the state rho shared by Alice and Bob, along with the measurements that they perform for each possible question that they might receive. Given that G is an XOR game, Alice and Bob always answer binary values, so there are two measurement operators associated with each measurement they could perform, corresponding to the values 0 and 1. If we think for a moment about the expression written on the slide, we find that it equals the bias of the strategy. The reason is that if we were to expand out the tensor product of the differences of the measurement operators and consider the two possible values for f of xy, we would obtain a sum representing the difference between the probability that Alice and Bob win and the probability that they lose. That is, there would always be a minus sign in front of the terms representing a losing pair of answers, whereas the terms corresponding to winning answers will not have a minus sign. And now, if we define a sub x to be the difference between px0 and px1, and likewise define b sub y to be the difference between qy0 and qy1, then we obtain the simple expression for the bias of Alice and Bob's strategy that's written here. You can think of a sub x and b sub y as being Hermitian operator observables in the parlance of quantum mechanics, which are Hermitian operators whose eigenvalues represent the possible outcomes of a measurement. Notice that as we allow px0 and px1 to range over all possible measurement operators for a binary valued measurement, the operator a sub x ranges exactly over the Hermitian operators having spectral norm at most 1, or in other words, the Hermitian contractions, and likewise for qy0 and qy1. There could be multiple choices of measurement operators leading to the same Hermitian operator observable, but every Hermitian operator contraction can be represented in this way for at least one choice of measurement operators. Now, these operators don't tell us what the probabilities are for Alice and Bob's answers, but they do tell us what the probabilities are for Alice and Bob's answers to agree or disagree. So they do determine the bias of the strategy, as the formula shows. Now we're ready to state Tsirelson's theorem, which is as follows. Suppose that we have finite and non-empty sets, x and y, and suppose that we have a matrix M having real number entries whose rows are indexed by x and whose columns are indexed by y. Equivalently, we can view M as a linear operator mapping between real Euclidean spaces, one whose vectors are indexed by y and the other whose vectors are indexed by x, but it's probably more natural to think of M as a matrix in this context. The theorem establishes that two rather different properties of the matrix M are in fact exactly the same. The first is that the entries of M store the real number values that could possibly arise from an entangled strategy that we saw in the previous slide, specifically in the expression we obtained for the bias of the strategy. More precisely, this property of the matrix M is that the entries of M are given by the inner products of some state rho, which acts on a tensor product of any two complex Euclidean spaces A and B, with the tensor product of Hermitian contractions A sub x and B sub y, for x and y naturally ranging over the indices of the matrix. In other words, the entries of M tell us exactly what we need to know about a given entangled strategy to compute its bias for whatever XOR game with question sets x and y we might wish to consider. It's important to note that this statement requires nothing at all of the spaces A and B other than that they're complex Euclidean spaces. They could have any dimension whatsoever. This seems like a pretty complicated condition on M, as we could range over any choice we wish for the entangled strategies, and entangled strategies for nonlocal games in general can be quite complicated. The second condition is remarkably simple. It says that it is possible to put M and the adjoint of M, or equivalently the transpose of M because M is real, on the off-diagonal blocks of a 2x2 block matrix, and put some choice of matrices R and S having diagonal entries equal to 1 in the diagonal blocks in such a way that the entire block matrix is positive semi-definite. And that's it. It's really quite striking that these two conditions are completely equivalent. So, if you want to know if there exists an entangled strategy that yields a given collection of values that describes how well that strategy performs in any XOR game of the appropriate size for any dimension whatsoever of the spaces A and B, all you need to do is determine whether or not there exist R and S with diagonal entries equal to 1, such that the block matrix in the second statement is positive semi-definite. And that, as you might anticipate, will yield a pretty simple semi-definite program for computing the bias of any XOR game. But we'll delay the discussion of that semi-definite program until the next lecture, and for the remainder of this lecture, we'll focus on proving the theorem. Before we move on to the proof, a brief comment is in order, and that is that in the second statement of the theorem, it isn't important whether we work over the real numbers or the complex numbers. That is, the second statement is equivalent to the statement written here, which is exactly the same as the original second statement, except for the requirement that the matrices R and S have real number entries rather than complex entries. And it's pretty easy to see this. Obviously, if the alternative second statement written here is true, then so is the original, because real positive semi-definite matrices are special cases of positive semi-definite matrices with complex number entries. On the other hand, if the original second statement is true, then we can quickly get our hands on suitable choices for R and S that have real number entries. Specifically, let's suppose that R0 and S0 are positive semi-definite matrices that may have complex number entries that satisfy the requirements of the original second statement, meaning that by plugging these matrices into the 2x2 block matrix with M and M adjoint on the off-diagonal blocks, we obtain a positive semi-definite block matrix. And of course, R0 and S0 have diagonal entries equal to 1. We may then define R and S as is written here. R is the average of R0 and R0 transpose, and likewise for S. These have to be real matrices because transposing a positive semi-definite matrix over the complex numbers is the same thing as performing the entry-wise conjugate. So every entry of R and S is the average of some complex number with its own complex conjugate. And the reason why R and S satisfy the requirements of the second statement is that the transpose is a positive map. And so the new block matrix, being the average of a positive semi-definite block matrix with its own transpose, is positive semi-definite. So R and S can be real or complex, it doesn't matter. In order to prove Tsirelson's theorem, we're going to make use of an interesting tool, the Brauer-Weyl operators, and you can think of them as one way to generalize the Pauli operators so that there are more of them. We can pick any positive integer n that we want, and let's take z to be C2, or any complex Euclidean space of dimension 2. The Brauer-Weyl operators of order n are 2n plus 1 operators, all acting on z tensor n, that are defined as you see written here, where we're using standard names for the ordinary 2x2 Pauli operators. With the exception of the last one, the odd-numbered ones look like sigma z tensored with itself some number of times, tensored with sigma x just one time, and then tensored with the identity some number of times. The even ones are similar, except it's sigma y instead of sigma x, and the last one is just sigma z tensored with itself n times. You'll note that they're all both unitary and Hermitian, and to understand the key property of these operators, it's helpful to look at an example, which we will do presently. And n equals 3 will be just fine for the sake of an example. When n equals 3, there are 7 Brauer-Weyl operators, and here they are. The main point of the construction is that these operators anticommute in pairs, and that's because sigma x, sigma y, and sigma z anticommute in pairs. And of course, every operator commutes with both itself and the identity operator. As you look down the list, you'll see that the first one very clearly anticommutes with all of the others, and likewise for the second. And then the rest of them have a similar pattern except with an extra sigma z in the first tensor factor. So you can show that they all anticommute with one another by a similar argument. And this sort of reasoning can be turned into a proof by induction on n that these operators always anticommute in pairs for any choice of n. Now let's take a look at two specific properties of the Brauer-Weyl operators that are relevant to the proof of Tsirelson's theorem. The first property is that if we take any real linear combination of the Brauer-Weyl operators of a given order n, where the coefficients form a unit vector, here denoted by lowercase u, then the result will be a unitary and Hermitian operator. The second property is that if we take any two real linear combinations of the Brauer-Weyl operators, with coefficients represented by vectors u and v, which aren't necessarily unit vectors in this case, then the inner product of the resulting operators will always be 2 to the n times the inner product between the vectors. These properties aren't difficult to prove, and we'll take a moment now to prove them. For the first one, let's start by observing that because every Brauer-Weyl operator is Hermitian, any real linear combination of them is also Hermitian. This part of the statement is trivial. To prove that the linear combination is unitary, we'll use the fact that the Brauer-Weyl operators anti-commute in pairs. Also, because these operators are all both unitary and Hermitian, they must square to the identity. So, if we take the linear combination and multiply it to its own adjoint, which is the same as just squaring the operator because it's Hermitian, we obtain the formula shown on the slide by multiplying everything out and dividing the terms into two sums, depending on whether the indices are equal or not. By the anti-commutation of the Brauer-Weyl operators, the second sum must be 0, and the first sum simply evaluates to the identity by the fact that u is a unit vector and every Brauer-Weyl operator squares to the identity. So, the operator given by the linear combination times its own adjoint is the identity operator, and therefore it's unitary. For the second fact concerning the inner product of real linear combinations of the Brauer-Weyl operators, this has nothing to do with the anti-commutation property. It's really just a simple consequence of the fact that the Brauer-Weyl operators are pairwise orthogonal. Specifically, they satisfy the orthogonality relation you see here. Computing the inner product of the linear combination divided by 2 to the n immediately yields the inner product of the vectors u and v. Any collection of tensor products of Pauli operators would have a similar property. Now we're ready to prove Tsirelson's theorem, and in order to keep our notation as clean as possible, let's assume that x is the set of integers from 1 to n, and y is the set of integers from 1 to m, for any choice of positive integers n and m. We'll start by assuming that the first statement is true for a given choice of m, and our aim will be to prove that the second statement must also be true. This is the easy direction. We will directly choose suitable matrices R and S using the state row and the operators A1 through AN and B1 through BM that tell us how some entangled strategy performs for an XOR game. And the way that we'll do this is to first define an operator K like you see here, and we'll take a moment to try to parse that description. The rows of K are vectorizations of certain operators defined by the state row and the Hermitian contractions A1 through AN and B1 through BM. So that's why the space K axon is A tensor B tensor A tensor B. That's what we get when we vectorize an operator that maps A tensor B to itself. There are n plus m rows, so the space that K maps to is just Cn plus m. But here I've written that as the direct sum of Cn with Cm, just to stress the block structure of K times K star, which is then a positive semidefinite operator acting on the direct sum of Cn and Cm. And now what we're going to observe is that if we write K times K star as a block matrix, we're going to find m and the adjoint of m on the off-diagonal blocks. And the diagonal blocks have to be positive semidefinite operators, and we'll call them P and Q. To verify that we get m and the adjoint of m on the off-diagonal blocks, we can compute the relevant inner products between the rows of K, and we see that we get one of the entries of m. And this is exactly why the rows of K were chosen like they were. If we look at the diagonal entries of P and Q, then we're taking the inner product of one of the rows of K with itself. And you can see from the expression that we get that this value can't be any larger than 1 in both cases. We can now choose R and S that satisfy the second statement of the theorem by simply adding non-negative numbers to the diagonal entries of P and Q to make them all equal to 1. And that is the first and the easier of the two implications we need to complete the proof. Now let's consider the second implication, where we assume that statement 2 holds, and our goal will be to devise a strategy, or more precisely, a state row, and Hermitian contractions A1 through AN and B1 through BM, so that the first statement of the theorem is true. And by the remark made just after the statement of the theorem, we are free to assume that R and S have real number entries, and that assumption will be important for the next step, which is to recall that a real positive semi-definite matrix has to be the Gram matrix of some set of real vectors. And so we can choose real vectors u1 through un and v1 through vm, so that our 2x2 block operator is the Gram matrix of this collection. And that means that the inner products between the u and v vectors have to agree with the entries of M. The inner product between any two u vectors corresponds to some entry of R, and likewise the inner product between any two v vectors corresponds to an entry of S. Given that the diagonal entries of R and S are equal to 1, we see that u1 through un and v1 through vm are necessarily unit vectors. Given that there are a total of n plus m of these vectors, and they're all real as just mentioned, there's no reason why we can't just take these vectors to be from Rn plus m. And at this point, we're going to pull out our main weapon, which is the Brauer-Weyl operators. Choose capital N so that 2 times capital N plus 1 is at least n plus m. Let z be C2 as before, and let v1 through vn plus m be the first n plus m Brauer-Weyl operators of order capital N. We can now directly define a state rho and Hermitian contractions a1 through an and b1 through bm, for which the first statement of the theorem must be true. First, we'll take each a sub j to be the real linear combination of the Brauer-Weyl operators given by the vector u sub j, and likewise for each b sub k arising from the corresponding vector v sub k. But in this case, we have to transpose the Brauer-Weyl operator. That's either going to negate the Brauer-Weyl operator or do nothing at all to it, but it doesn't matter. We're just putting it there on purpose because we're anticipating that a transpose is going to be coming later. Anyway, given that each of these operators has to be unitary and Hermitian, which is the key property of the Brauer-Weyl operators in this proof, we find that each of these operators is a Hermitian contraction. By the way, given that these operators are not just Hermitian contractions but Hermitian unitaries, we see that there's actually only one choice for Alice and Bob's measurement operators in any strategy that would yield these Hermitian unitaries. The measurements have to be projective, corresponding to the +1 and -1 eigenspaces of a sub j and b sub k. The state rho is just the canonical maximally entangled state. And now, if we tensor a sub j with b sub k, and then take the inner product with rho, we get 1 over 2 to the n times the inner product of a sub j with b sub k transpose. It's another instance of the vectorization identity that we so often use. Transposing b sub k cancels out the transpose in the definition of b sub k, and using the orthogonality property of the Brauer-Weyl operators that we observed before, we see that this scaled inner product is simply the inner product of u sub j with v sub k, which is the jk entry of M. And that's what we wanted, and so we're done. We're going to use this theorem in the next lecture, as I mentioned before, so this isn't the end of the story. For now, let's just observe the following implication of the theorem, or really its proof. And that is that if we have any XOR game G with question sets X and Y, Alice and Bob always have an optimal entangled strategy where they share capital N qubits in a maximally entangled state, for n being the floor of the size of X plus the size of Y divided by 2. That's a lot of qubits in some sense. It's exponential in the length of the strings needed to describe the elements of X and Y, but it is a fixed number that's needed for optimality, and that's not something that's true in general for general non-local games. There are also non-local games for which maximally entangled states cannot be optimal, but that never happens for an XOR game. That's all for this lecture. Comments, corrections, and questions are welcome as always.